Hello there guys, and welcome back to another epic Inexorable maths video. In this video we're looking at the birthday paradox and we're going to explain what's going on there. The birthday paradox is really weird. What it says though is it says that in a room of just 23 people, the chances that 2 or more of those people share the same birthday is more than 50%. Yeah, and it's true, it's genuinely true. In a room of 23 people, the chances that 2 of them share the same birthday is more than 50%. It's called a paradox because it sounds so incorrect. It sounds like, no way, you need way more than 23 people in order for this to happen, but actually you don't. And I'm going to show you and prove it to you using maths. And this is true, it works in practice, as long as you assume that the distribution of people's birthdays are completely even, which there's no reason not to. I mean, roughly speaking, it's absolutely the case. So let's look at why. Okay, first of all, we're going to work out the probability that in a room of 23 people, no one shares the same birthday. Not a single soul. You walk into a room of 23 people and not a single person has the same birthday as anyone else in the room. Let's work that out. Well, in order to work that out, all we need to do is work out the probability that a specific individual does not share the same birthday with another person. That's really easy to work out. What's the probability that you yourself walk up to someone on the street, ask them what their birthday is, and they have a different birthday to you? Well, if we don't count for leap years, the probability of this happening is simply 364 divided by 365. This is the probability that they do not share your birthday. And of course this makes sense, there's 365 days in a year, and there's 364 days that are not your birthday, which means the probability that you do share the same birthday is 1 in 365. Probability that you don't is 364 in 365. So this is a probability that 2 people in the room, if you specifically say you and you, that's the probability they do not share the same birthday. But you're not just saying, hey, you there and you there, do you have the same birthday? You're not doing that. You're saying, you there, do you share the same birthday with any of these other 22 people? And then you're saying to the next person, hey, do you share the same birthday as any of these other 22 people? And then you're saying to the next person, do you share any of the same birthdays with these 22 people? And actually, there's a lot more opportunities for people to share the same birthday as you might think. So the number of ways, the number of groupings of 2 individuals in a room of 23 people is actually 23 choose 2, which some people will write as 23 choose 2, like that, almost like a vector. 23 choose 2, I'm going to leave a link in the description to another video where I was talking about choose and the choose operation. It's the handshake video. It's very similar. 23 choose 2 means if you're in a room of 23 people, how many ways, how many combinations of 2 of them are there? And actually 23 choose 2 is equal to 253. Okay, so it means that if you walk into a room of 23 people, there are 253 different pairs of people that can happen. In general, n choose r, which is the typical kind of general form of the choose operation, means if you have n objects, how many ways can you arrange r of them? And it's really the same thing. If you have 23 objects, how many ways can you arrange 2 of them? If you have 23 people, how many ways can you have, and how many pairs of 2 of them can you get? It's 253 you can do it on a calculator. There is also a formula I won't go into in this video because I speak about it in another video, again, that I'll leave in the description. So the whole point is that there's actually not just, hey, you and you, do you guys have the same birthday? It's actually 253 different opportunities for people to share the same birthday. So the probability that in a room of 23 people, no one shares the same birthday, it means that you have to take the chance 364 out of 365 253 times consecutively, and none of them have to have the same birthday. So actually, the probability that no one shares the same birthday in a room of 23 people is 364 divided by 365 times by itself 252 more times. So it's to the power of 253. This is the probability that no one shares the same birthday in a room of 23 people. And if you actually just type this in on a calculator and compute this, which is what I'm going to do right now, because if I remember rightly, it's a really not very nice decimal that I cannot remember off the top of my head. But if you actually do this computation, you end up with the number 0.499522846, etc. But this is the probability that no one in the room shares the same birthday, which means the probability that 2 or more people share the same birthday is 1 minus that. And if we do 1 minus that number on a calculator, you end up actually with 0.5004775154, which corresponds to a greater than 50% chance. You can see here. This here is the probability that in a room of 23 people, 2 of them or more share the same birthday. It's greater than 50%. And that's the birthday paradox, and that's really what it says. It's really interesting. As you increase the number of people, when you perform n choose on, when you perform 23 choose, and then, or an increasing number choose 2, so let's say 30 choose 2, or 40 choose 2, this number increases by quite a lot, and you're raising it to higher powers. It ends up being that once you get to about 70 people, if you're in a room of 70 people, the probability that 2 people or more share the same birthday is so close to 100% that you can almost guarantee it. So if you're in a room of more than 23 people, you could bet that 2 of them share the same birthday. 2 or more of them share the same birthday. Maybe 3 of them do. Maybe 4 or 5. Who knows? Well, thank you guys for watching this video. I hope you found it interesting as I do, and I'll see you in the next video. That was the birthday paradox. See you later.